So when you give us one of these parametric equations, right?
Yeah, right.
And then we eliminate the parameter.
Sure, okay.
So we're like solving for either x or y, or solving for t and then plugging it into the other. Does it matter which one? Did we just pick the easier one, I guess?
Yeah.
Okay, so it doesn't matter because like the book only has like one of them listed, and I was wondering like if it mattered.
Yeah, like more often than not, it was a lot of times what you're doing is you're eliminating. A lot of times, like x, the function for x is t. In that case, it's really easy. Just every t replaces with an x. You know. And so and you know, like another thing that you might have to do, you know, so I think I'm planning to do an example of that today. But it's something that you would need to do in the next class, the multivariable calculus. Sometimes you have a curve, and you have to parameterize it.
Okay, so work backwards.
Yeah.
All right. I have a question. So, like, based off of what you were saying, the x and y, right? Isn't it just if you solve for y, wouldn't it just be the reciprocal of x if you were to solve for x?
Depends on the function.
Because if x is t, and both are in what if it's 2t or whatever, right? So like the first one was t squared minus 2t
Plus 2t.
plus 2t, and y equals.
That was on the last one though. I was just touching up on it.
Well, I wasn't here for that all.
Yeah, no, I was trying to help you out.
Well, let's go through one of those questions. 7-1.
7-1.
7-1.
So something from here.
Yeah, number 1. That's the one.
Number 1. Oh, this one. So in the following exercises, sketch the curves below by eliminating the parameter t. Give the orientation of the curve. Ah, that's good. I haven't talked about orientation. So glad you asked. So, so for example, here's a parameterization of a curve where x is t squared plus 2t and y is t plus 1. Typically, I might have some sort of a restriction on t, but since no restriction was stated, you can assume that t will assume all possible values.
Okay.
So positives, negatives, all possible values. And so I guess for emphasis, I'll just say for all t, right? So if no t is mentioned, it's implied that we're talking about for all t. And what? Sketch the curve by eliminating the parameter. Okay. Yeah, it's not immediately obvious to me what this graph looks like, but if I notice that I can eliminate the parameter by noticing that t is equal to y minus 1.
Yeah,
So question.
Yeah.
What does parameter mean?
Parameter is, so the parameter is t. T is the parameter because it's determining x and y.
Okay.
Yeah. In fact, actually, one thing I mentioned last time, when you weren't here, is a lot of times I like to express this in a different way.
Okay.
Right? This is kind of a little more sophisticated way of saying the same thing. I define this new function, which I'm calling r. R is a function of t. So it's a function of a single variable, but the output is not a formula, for another real number. Rather, it's a vector. The output is a vector. This is a vector-valued function, which I would write as with an x-coordinate of t squared plus 2t and a y-coordinate of t plus 1. This is a vector-valued function. For each t, each real value t, I get a two-dimensional vector. And in general, I'd say this vector could be represented as mapping a real variable to a two-dimensional real variable, a vector with two real entries. And I like to me, I think in this case, the parameter is the domain. I think it's easier for me to describe what the parameter is in this context, right? And the parameter is what's determining, the x and the y. And when I graph it, notice that when I graph it, I have an x-axis, I have a y-axis, but I have no t-axis. So the parameter is not shown on the graph, all right?
That's what I was trying to explain to you when I was like, man, you said something about it.
So,
Yeah.
quick question.
Mm-hmm. Mm-hmm.
I'll be in other classes and I'll be like, hey man, I mean, the teacher just said something so stupid, simple, and you're not getting it, right? I don't want to be that guy right here.
Yeah.
So, parameter.
Yeah.
To see if I got it right. Parameter is the T,
Yes.
which is the domain for a vector function.
Yes.
The vector function comes from the series of equations for x and y.
Mm-hmm.
So, would the same thing be said? So, for over here, right?
Mm-hmm.
If I'm solving for t,
Yep.
would it not be the same thing as? So eventually, the way we did it, or we tried to do it, was like solving a system of equations using substitution.
Yep.
Is that what we're doing in this?
Yep.
Okay.
Exactly. Mm-hmm.
I get that, but how does that, what does eliminating the parameter mean?
It means substitution.
Okay.
Yeah.
Cool.
Yeah. Yeah. And what we did last time, right? It might help to have a little bit of context to this. Like, before you start eliminating a parameter, like, what does this mean? It means that you can, I can take some values of t, like, if t equals, oh, that's a bad pin. If t equals 0, you can plug in 0 and see what vector you get. The input is a real number, the output's a vector. That's why it's called a vector value function. You plug in a 0 for the parameter, and I'm looking over there and plugging in 0, and I get 0 plus 0 comma 1 in this case.
Because there's an equation for both the x and y.
Mm-hmm.
Vector value function, you said?
Mm-hmm. And technically, I should be, as the parameter increases, you're going to get a sequence of vectors that are pointing to different points on the curve, right? So, like, I can see that this is a point on the curve, corresponding to a value of 0 for the parameter. But as t increases to, say, 0.5.
I'm sorry, can you say that again?
Yeah, so when the parameter is 0, the vector is pointing to a point on the curve.
From the origin, the
Yeah.
vector to that graph,
Yeah.
when you eliminate the parameter.
At this
Got
point, I can now see that this is a point on the curve.
Okay.
And furthermore, this is the point that corresponds to 0, to t equals 0, right? I usually won't label it, but just for clarity, I'll just say t equals 0 right here. And as t increases, t could really be anything.
Right.
But if I was to bump it up to 0.5, I'd be plugging in 0.5, be squaring a 0.5, adding it to twice 0.5 for the x coordinate, and taking 1. Yeah. So let's see what we get there. So it's going to be a quarter plus 1. So yeah, you're right, 1.25. The y coordinate would be 1 plus 0.5, so 1.5. So that means that as t was increasing from 0 up to 0.5, the curve, it should be kind of connected in somewhat of a smooth way. But it's going to end up at, let's see, I need some labels here. If this is 1, let's say this is 1 and that's 2. That means that I'm at 1 1/4 and 1 1/2. Maybe about right here, I'll say. So as t was increasing from 0 to 0.5, these two dots got connected somehow, right? If I'm going to investigate how they get connected, I can plug in more points, or if you want to get really fancy, you can find the derivative and the second derivative and see the concavity and slope and that sort of thing, which is also something we talked about last time. But I think I can get a pretty good sense of it just by plugging in numbers. If I plug in 1, what is that going to be, 3 now?
Right. 2.
2. So that means I'm over here, right? About here maybe? Looks like it might have been speeding up actually.
Right.
So the t is Here, t was equal to 0.5. Here, t is equal to 1. So I'm to cover a greater distance in the same amount of time. If I think of t as time. It's not necessarily time, but that is a typical parameter, is time. I guess that's why they use t. Yeah, and then I'll just do one more computation. 2.25 plus 3, so 5.25, and 2.5. All right. So just based on the several calculations, it looks like I'm going to be somewhere around here, I suppose. That's when t equals 1.5. And you know, t could even be a negative number, right? But after plotting these points, it gives me the sense of a curve that looks something like that. And if I were to guess, I imagine it would probably just continue on something like that. I'd have to plug in negative 0.5 to know for sure. And that kind of gives me a sense of what the graph looks like. But sometimes, another way to see what the graph looks like is to eliminate the parameter. And by elimination, it's just substitution. And if I can, I'll have an equation in just x and y. It might be an equation that's familiar to me. Because certain equations, you'll quickly recognize the graph, right? So that's where we're at. This question is not asking you to do any of that. It's asking you to do substitution. So yeah. So since t is y minus 1, I can substitute. And now it's a little more clear that I have a quadratic equation.
Sideways.
A sideways quadratic equation, right? Usually it's y equals, right?
Right.
This is x equals. So once I get to this point, already I can see that this is a piece of a parabola, right? If I was to continue picking values of t, I think it would probably start to loop around like this, right, with the negative values of t. They also want you to give the orientation of the curve.
Horizontal?
Well, orientation of the curve. I don't think they're referring to that. They're referring to, like, whenever you parameterize a curve, I'd like to indicate the direction of increasing t. If I didn't show you all this, if I didn't have these labels right here, like, as I pick larger and larger values of t, am I getting points going this way, or am I getting points going that way?
Oh, so positive? Is that positive or negative?
Positive. So the way I indicate orientation of the curve, I can just put a little arrow on it. It's kind of in the middle.
Okay.
If the arrow's on the end, that means it keeps going.
And that's not to be confused with any kind of vector. That's just the orientation.
It's not a vector, yeah.
Okay.
I'm just saying that as t increases, you're moving in that direction along the curve.
That's what confused me in the book. They got the arrow, but I thought it was like
Right.
vectors, and I was confused. Yeah.
Yeah,
So-
not a vector.
These, the R, R0, the vector value function, right? Are the components
Yeah.
of that.
Yeah. I made a big deal about how these are vectors, but I haven't actually drawn the vectors.
Right.
Right?
Right.
This vector is right here, that green. This vector is right here.
Right.
This vector is right here. And this vector is right here. So, this is a vector value function, but I'm just using the vectors, the head of each vector to describe the curve. Right? And put this over here so I don't pick it up again.
He picked it up and tried to show you how to do it. Oh no, yeah.
Yeah.
It's all my fault.
It is.
Dude, so if I fail this next test, it's all over.
Yeah. In 7.5, it's on conic sections, right? We'll be able to talk a little bit more about, more precisely what kind of a parabola this is actually. But nonetheless, I can kind of think by analogy, you know. I can see that this is going to be, I know that -1 is like a transformation.
Yeah. So down.
Yeah, yeah. Well, actually, it's going to be up.
Up. Oh yeah, because if it was.
You know what I mean? And also, too, I can see, so the graph of this is going to be a transformation of this one. So it's the graph of this one transformed.
Mm-hmm.
And this, the graph of this one looks a lot like the graph of this one.
So the turn on the side.
Yeah, it's being reflected. When I interchange the x and y, that's a transformation of reflecting it over the line y equals x. And I just wanted to look at this one because I think I can graph this one. You know, because this is x times x plus 2. So my logic is this. The graph of this guy is a parabola with x-intercepts at 0 and
Negative.
-2. So here's -2. Here's 0. Is it opening up or opening down?
Up.
Yeah, because the first coefficient is positive. So the graph looks like this. Therefore, the graph of this one is very similar to in shape to it, but it's been reflected over the line where y equals x. So these x-intercepts are now y-intercepts. And it's going to be opening to the left or the right.
Right.
Yeah. And when I put this, and then this the graph of this equation is going to be a transformation of this one. You see how that's because it's a y minus.
Yeah.
That's going to affect the y coordinates, right? You know, and so, you know, over here when I was squaring 0, you know what I mean? Well, when am I squaring 0? When y equals 1. So that means that this graph is really just that one. I guess I can put it right here. It's really just that one, just shifted up by 1. Let me think. Y equals 1. I guess so. Yeah, this is 1 right here. I'm going on faith here. Well, there's 1. This is 3 now. So this point went up by 1. This went up by 1. That's at 2. So now it's at 3. This is at 1 and 3. So it seems to me like it should look something like this. It'll hit the x-axis eventually. Is that agreeing? That's not agreeing with what it is. That is not agreeing with what I wrote.
So again, if we did the equation after t equals y minus 1, right?
Mm-hmm.
If we factored all that out,
Mm-hmm.
it would be the y squared minus 2y
Yeah.
plus 1.
Yeah. Yeah.
But then that's
I was trying to avoid that.
but then you would have to add the 2y minus 2, right?
Yep. Yep. Mm-hmm.
So
Exactly.
y squared minus 2y plus 1 plus 2y. So then this is y squared minus 1, which is
I guess
not
I was able to see the x-intercepts by factoring.
right.
Maybe I can find the y-intercepts by factoring as well. I'm getting a little bit uneasy because it's not matching with what I expected. I have two terms. They both have a y minus 1 attached to it.
Right.
I'm going to factor out a y minus 1. What I have left with is another y minus 1 and a 2. That's y minus 1 plus 2.
Okay.
So in light of this, I can now see that I have y-intercepts at 1 and at -1. So I must have confused myself. I guess it went down actually, not up. So yeah, somehow I confused myself.
Yeah, because that y minus 1 squared becomes plus 1.
Mm-hmm.
So then
Yeah. Okay. Yeah. So yeah. Okay. So yeah. So the y-intercepts actually are at 1 and -1. So the graph actually looks like that, which agrees more with what I drew here. So now I can see, I can make a more complete graph in light of that without even plugging in any more t's. is going like this. And I might put in one more arrow. These are all negative t's, but as
Oh,
t
just to
increases,
show.
it's going that
Okay.
way, right? Is that okay? That's how these work.
I have a question for the
Mm-hmm.
7.2 now.
Okay.
We got time for that?
Sure, yeah. Let's see it.
Can you show me how to do number, whatever, 67 from 7.2?
67, huh?
Yeah.
Something like this.
Yep.
So for the following exercises, determine the slope of the tangent line. Then find the equation of the tangent line at the given value of the parameter. Nice.
67. Jeez, man, really?
So in this case, x equals cosine t, and y equals 8 sine t, and t equals pi over 2.
So when it gives you what t is, what is that really doing? I mean,
Well, because it's
Just
just the
saying at that
instructions.
point. Yeah, it's just saying
at that specific point.
Yeah.
What
So,
is the tangent line equation?
so t can still, just like before, can assume any possible value.
Right.
But they're specifying a particular t to specify a particular point on the curve,
Okay.
right? Like when t equals 0.5, that's that specific point on the curve.
Okay. Right.
And at that point, I'd like to know the slope of the tangent line. That's the hard part. Once you know that, then finding the equation of the tangent line should be pretty straightforward. All right? At the given parameter. This is the parameter. This is the given parameter in this case is pi over 2.
Okay.
The first thing that jumps out at me, I see sine and cosine.
Yeah.
I'm thinking circle. Because in a unit circle, the x-coordinate is given by cosine, the y-coordinate is given by sine.
Right.
But that's not sine, that's 8 times sine. So it's going to be kind of circle-like. What is the graph of this looking like if you're thinking of the unit circle?
0 and
Just the eight times bigger.
8, no, 0 and 4.
Yeah, it's going to. This is actually like a transformation
Yeah.
on y.
Yeah.
I'm literally stretching it in the y direction.
8 times bigger. Yeah.
So this is going to be in an ellipse with an x-intercepts at 1 and -1, y-intercepts at 8 and -8.
Right.
So we're literally just stretching it vertically. That's what we're doing there. And when t equals pi over 2,
1 times 8.
oh gosh, I don't think I even need anything for that one. Pi over 2, this is like, because x is going with a cosine and y is going with a sine, it's literally working just like the unit circle. It's just it's not a circle.
Right.
But at pi over 2, that means I'm looking at this point up here.
Tangent to 0.
Yeah.
Okay, yeah, that was a bad example. So, like, let's do an example where, like, when you have to dy over dx.
Yeah, sure. Well, we can do it again at, let's say, pi over 3,
Okay, yeah.
You know what I mean? But nonetheless, let's pretend that, let's pretend you're kind of working your way through this blindly. It didn't occur to you that this was an ellipse,
Right.
and therefore it didn't occur to you that the slope is obvious. You know what I mean?
Okay.
Then what you would have done is you would have said, and I prefer this other notation, right? This makes me feel like I'm dealing with two different things, but there actually are one entity unto itself.
It doesn't have to necessarily be R.
Yeah,
It doesn't have to.
It could be F of T. And one of the things we talked about, actually I probably spent more time than I needed to on it. I could have just told you guys the result, but I wanted to prove it. So we got into the nitty gritty. And what we discovered after the dust settled is that you can find a tangent vector, and it's pretty straightforward. call this the derivative of this vector value function. And it's really just the derivative of each of these coordinate functions. So the derivative of cosine is?
Sine.
Negative sine.
And the derivative of 8 sine t?
8 cosine t. So the slope is 8 cosine t over negative sine t, right?
And by the way, let me ask a follow-up question. Since we were talking about the orientation of the curve, what is the orientation of that ellipse?
It just goes this way, right?
Yeah.
Counterclockwise.
No,
Yeah.
because you started pi 0.
Oh,
It's 1. If you go to pi over 2, you're going this way, so it's counterclockwise, not clockwise. Is that what
I
you
just
said?
said counterclockwise.
All I saw was this, and I thought it was going clockwise.
Yeah, if you're not sure, you just plug in some numbers. Like you said, you plugged in 0, you plugged in pi over 2. So you must be going in this direction. That's the orientation. And all the way around, right?
So would that be? So over there we said positive.
Yeah.
Would that be negative now?
Well, I mean,
Well,
positive.
theta is
Positive in what sense? I never said that the orientation was positive. I just said
So
the
you just
orientation-
said you
just
just
going that way.
Oh, okay.
It literally just draw the arrow.
So the arrow is indicating the positive direction.
But how do you verbally articulate
Yeah, if I can't see that, how do you express that to a blind person?
that?
I would just plug in a couple numbers. If you plug in 2 numbers, one's bigger than the other,
It's going that way.
it's going that way. Yeah.
Try it.
But it occurred to me to mention this thing about the orientation of this, because when you get to this point, you're going to get a tangent vector. Which way is the vector going to be? It'll be a tangent, but is a tangent vector going this way, or is it a tangent vector going that way? Right? It actually goes in the same direction as the orientation.
Always.
Because the limit is as it's approaching.
Yeah.
Is it always or this
Always.
specific?
Always. I was checking to make sure I wasn't lying to you if I plug this in. Because you see, like when I plug in pi over 2, right? If I plug in into the derivative, pi over 2, what I get,
0.
yeah, that's a 0, isn't it?
Yep. No 1.
No, that's
Negative.
that's
Oh
positive.
yeah, pi over 2. We're not plugging 0, plugging
Yeah.
over 2. Yeah, so that's negative 1. And,
What?
0.
right,
The sine of pi over 2 is
1.
not on that. Oh yeah. Oh man, I'm thinking 8.
Yeah.
Yeah. Yeah. Try it.
Yeah. So the vector, this is going to be a tangent vector, and it's right there. Right? I guess if we were to go back to the one we did before, and we found that derivative of the vector value function,
Right.
then if I had plugged in 0.5, you would be getting, now that is a vector. But if you plugged in a point like -3, which would be a point somewhere around there, you'd get this vector right here.
Right.
See?
Wait. Okay. Yeah. Now I am confused.
Mm-hmm.
Aren't these
Still x of 1.
vectors? Wouldn't they be applied specifically to this eclipse, right?
Ellipse.
Ellipse. Yeah.
Yep. Mhm.
So wouldn't the sine of pi over 2 be 8?
The sine of pi over 2?
Yeah.
That's the, yeah.
That'd be 1 on the unit circle, right?
Yeah, on the unit circle. That's not the unit circle.
I know, since we're specifically talking about this,
Yeah.
wouldn't that value be 8? Or -8?
No, we're not using that. I'm still using the unit circle as you know it. Here's the unit circle.
Right.
And it's still a circle.
Right.
So the sine of pi over 2 would be 1. Right? And the cosine of pi over 2 would be 0. So what I'm plugging in here is 1 times -1
Yeah.
and 0 times 8.
So, okay, that first vector is pointing to
Yep. And what we discussed is also not only like the underpinnings of this, but also if I want to know the slope of a vector, how do I do that? How do I find the slope of a vector? And the answer was
Y over
the
S.
chain rule, right?
A squared plus B squared.
Mm-hmm.
C squared.
If you want to know,
A squared plus B squared plus C squared.
dy dx.
dy dx. Notice that
Same thing.
what this is right here,
Uh-huh.
that's actually dx. 'Cause I took the x coordinate, I took the derivative of it,
Right.
but I didn't take the derivative. I took the derivative with respect to t.
Okay.
And this right here, that's the derivative of y with respect to t. What I really want is not dy dt, I want dy dx. And that's a different thing,
Okay. Yes.
right? And the chain rule says that you can compute it by just simply taking dy dt divided by dx dt.
Comes out. The T's, DT's cross out.
Mm-hmm. Yeah, think of it that way. Yeah. So as expected, agreeing with what we were expecting, the slope is 0. Just it's right there.
So the slope is wherever that given point is that they want to calculate, plug into the
Yeah.
derivative.
Yep.
That's okay.
So if it was
Got it.
pi over 6,
Yep.
it would be negative.
This is where t equals pi over 6 over here. Yeah, I expect the tangent slope would be a negative number, right? Because it's decreasing, right?
Right.
And it seems to be pretty steep, so I would estimate it to be like -7, -8, or something like that. It looks pretty steep right there. You know what I mean?
Well, yeah, because there is an 8
Yeah,
there.
that's true.
Wait, what? Why is that where t equals pi over 6? I thought we were back to the, wouldn't it be on the unit circle?
Yeah. Pi over 6 is right here.
Right, so it wouldn't be like 7 or 8, right? It's still.
I don't know. Let me think. When t equals pi over 6, we did do a transformation. So this point has been actually pushed up by a factor of 8. So maybe it might be a little higher than what I drew right there. I guess if I want to know for sure, I would plug not into the derivative, but into the original function,
Right.
pi over 8. I mean pi over 6.
Pi over 6 would
Getting confused. So that would be 3 over 2. That would be half of 8, so 4. The y coordinate would be 4 exactly. So yeah, so I think if this is 4 right here, right in the middle of 8, then it should have been actually this point right here. That's the one I should have picked if I did it to scale. So maybe it won't be as steep as I thought, but it's still going to be pretty steep, right?
Right.
And I can see exactly what the slope is by just plugging in pi over 6 here and here, see what numbers you get, and divide just like we did over there. So,
4 root 2, 2.
What? What'd you say?
Well, so the sine of pi over 6
yeah.
is 0, 1. So
Yeah.
1/2, yeah. The cosine is root 2 over 2.
Root 3 over 2.
3 of them, sorry. 3 over 2.
Times 8.
But then it'll be at 4. So the answer's like, well,
In this case, I would have 4 root 3 divided by -1/2,
yeah,
right? Also known as
Multiply. Yeah.
8, 3,
whatever that is.
bigger than 8, negative 8, smaller than negative 8.
Wait a minute. But if that slope is negative, that means the line is decreasing, right?
Mhm.
But you said the tangent line is oriented in the same direction as your function.
Yeah, so you get, as a vector,
Right.
that vector is pointing this way.
How? Oh,
See how it goes to the left by -1/2 and up by that much?
oh, okay.
But as a vector, it's going like that. But the slope
Okay.
is not a vector
It's
at all.
not vector. It's not. Okay. Try it.
Yeah. That's how those go.
That's how those go.
All right.
Yeah, good problems. Yeah, and you can see how with parametric equations, ellipses are pretty, I don't know, I think it's pretty easy to write it out. If you wanted it to have like, just to be go from between ±2, I think you'd make a natural adjustment, you know? So I like how intuitive ellipses are with polar coordinates. Yeah. Excellent. So, anything else? We've been spending a lot of time, like, I think almost all the examples I've given you so far, I've given you parametric equations and asked for the graph, or maybe asked you to eliminate the parameter. But what if, and admittedly, I don't think they ask you to do a whole lot of that here, but it's coming, so.
It's coming. So why not do it right now, right?
Well, why not, yeah. Yeah, so like, what if I give you a curve and I ask you to parameterize it? I might ask you to parameterize.
Take the integral. Wait, no.
No, you don't.
Yeah.
You don't need calculus to parameterize.
Seems like you really don't like this. Oh, wait, no.
I'm just asking for a function, or a pair of functions, that'll do what I want it to do.
Can we walk through this? Like,
Mm-hmm.
so can you give us like an equation? Like,
So what I would do is
Or
I
a function.
would give you a curve,
have fun.
and then ask you to give me a parameterization, a formula for x and a formula for y, that'll generate that curve. Okay. So for example, I can give you
X squared.
how about
Wouldn't it just be the antiderivative?
Well, that's what I said. You said no.
how about this ellipse?
I need some more numbers on there though.
How about, let's say it goes from -3 to 3, and from 0 up to 4. So the center of this ellipse is clearly at 0, 2. Right? So if it was a circle, I could speak of a radius, but in this case, it's like I have like the biggest radius, if I can say such a thing, would be here. The shortest distance from the center would be here. And everything else just kind of varies in between those two
Would it not be?
values. Mm-hmm.
So the shift is what's getting me now because x would be like 3 cosine t
Yeah.
and y would be 2 sine t.
So a natural guess would be x equals 3 cosine t, and y equals 2 sine t.
But that doesn't account for the shift up.
But I think that's a pretty useful thing. So to the side, I think, okay, well, that's basically giving me this between 3 and -3 from -2 to 2.
So then
Mm-hmm.
if it's
That's
Okay, hold on.
-3, right?
Hmm?
It's supposed to be -3.
Yeah.
I know that.
Thanks.
is it x minus the x-intercept squared plus y minus the y-intercept squared?
What?
Square root of that equals r.
It's actually easier.
Cosine.
Transformations are pretty easy in parametric equations.
Can't you just put plus like plus k at the end of both of them?
Notice that when t equals 0, I get this point, right?
Yeah.
I get 3, 0 when t equals 0.
Yeah, that was 3, 2.
I would like it to be right here.
Yes. Can't you just say plus 2 at the end of the x value or the y value? Yeah.
Y value.
Yeah, plus k at the end.
Yeah. I think that'll do it. Just put
Plus 2
right there.
there.
So now when t equals 0, I'm still going to get a 3 for the x coordinate, right? But now the y coordinate, I'm still going to get a 0 here, but now I'm just going to add 2 to it. I shifted it up by 2. See? That's when t equals 0. And as t increases, this will kind of follow the same curve, just two steps higher, right? So, yeah, I think that'll do it. I have parameterized this curve. So those are a little more challenging if I just give you the curve and ask you to parameterize it. And by the way, parameterization is not unique. There's actually many ways the same curve can be parameterized. That's not the only way.
Okay. So basically, when you say parameterize it, it's kind of like we're identifying some function that we know or equation that we know, and
Yeah.
just writing the transformations of it, right?
Yeah. Like for example, here's another parameterization that comes to mind. X equals 3 sine t, y equals 2 cosine t plus 2. I think this will do the same thing, but with a different orientation.
It could be this way, right?
No.
No?
See this one, the x is still being stretched by 3. The y is still being stretched by 2. The y is still being shifted up by 2. But I've switched the x and y. In this case, the orientation is the same as the unit circle. But in this case,
It's clockwise.
yeah. Notice that when t equals 0, which point do I get on that ellipse? When t equals 0.
So sine of 0, and then
So x would be 0.
Yeah.
And y would be?
4.
So this point.
the other one is.
But over here, when t was equal to 0, you got that point.
Okay.
These are different parameterizations.
But the same.
Yeah.
Just different orientation.
And notice that if you plug in pi over 2, sine of pi over 2 is 1, so you get 3. Cosine of pi over 2 is 0, so you get 2.
So that sideways coming.
So this is when t equals pi over 2. So now, the orientation is actually clockwise in this case. So that's 2 possible parameterizations of the same curve. Right? I'll give you one more parameterization of the same curve.
Tangent? No, I'm joking.
How about,
Cosecants.
that's the same curve, different orientation.
Right.
How about this one?
Well, it's always between 0 and 1.
Yeah.
So it's basically should be the same as the top right one.
Which one?
The top right one.
What? This? What?
Yeah, that equation. Yeah,
Uh-huh.
because t is always 0 and 1.
Yeah.
So wouldn't it be? Maybe not. 536. Okay, never mind.
It's kind of a weird one. This is going to generate the same curve, but the orientation is a little trickier to describe.
Oh, like the orientation would be like a positive and then the same absolute value but negative, right?
Yeah. I mean, what's happening here, see, right here, notice that I can plug in negative values for t here.
Yeah.
Right.
I can plug in negative values for t, but when I plug in negative values
It's
for
gonna
t,
be
I'm actually
positive.
plugging in positive numbers
Yeah.
into sine and cosine. Right?
So when it just
So I'm never taking the sine or the cosine of a negative number in this case. Right? So for example, what might be kind of nice actually is if you had like if you could, I think you could put this on the Desmos and press like the play button and have it like actually like, you know, slowly start graphing it, and you can see the orientation a lot clearer.
So it would be like
Yeah.
positive, negative.
But what's happening here though, so I know it's going to be on, every single point's going to be on this path,
right.
right? But like for example, when t equals 0,
Right.
then it's going to be the same as that one over there, right? Because 0 squared is 0. So this is going to be a point corresponding to when t equals 0. And as t increases up to, say, not pi over 2, but the square root of pi over 2. When t gets up to square root pi over 2, then you square it to get pi over 2. Then you'll be right here. This is when t equals square root pi over 2. So the square is pi over 2, you know.
Mhm.
So at least from 0 up to this point, whatever that is, the orientation is counterclockwise, right? And as t continues to increase, it'll keep wrapping around, and you'll end up picking up the whole circle, right? But what's really weird is that if you plug in negative numbers for t, such as, what if I plug in like t equals negative square root pi over 2? What point would that be on this curve?
The bottom one? Or
No, it'll still be the top.
Right here, this is the point when t equals negative pi over 2, right here, right?
right.
So your instants are right. However, when you square it, this is going to actually become a positive pi over 2. This point is actually right there as well. And as t increases from this negative number and starts getting closer and closer to 0, it's actually going that way. So the curve is literally, so starting here, as t increases, the curve is actually going this way, stops here, turns around, and then starts going this way. Weird, huh? So the graph doesn't necessarily show the whole picture, you know what I mean? Because it could actually be, you know, backing up on top of itself and that sort of thing, you know? So pretty curious things can happen when you're exploring different kinds of parameterizations, right? But yeah, sometimes, you know, here's another basic parameterization, which might appear difficult at first, but we do this all the time in multivariable calculus.
We do this all the time in the class that you guys haven't made it to yet.
I'm going to specify a curve. The curve I have in mind is going to have 3 sections to it. It's going to start here. It's going to go along the x-axis up to here, let's say to 1. It's going to go along the quarter circle to here, and then back down to here. Follow? I want to parameterize that.
So can it be a piecewise function?
Exactly.
Oh,
That's exactly what it's going to be. So what I'm going to do is I'm going to define x piecewise. It's going to have 3 pieces to it. When t is between, let's say, 0 and 1. And then I'd like to pick up where I left off. So let's go from 1 to, well, my plan is to parameterize this with sine and cosine. So it's going to go from 0 to pi over 2. So 1 to 1 plus pi over 2. So it's tricky because I'm starting at 1. And then from 1 plus pi over 2 to 2 plus pi over 2. And to parameterize, I also have to give a formula for y. With the same three parts to it. But yeah, this is a case where I'm starting with the curve and trying to come up with the equations. So it's pretty common when you're dealing with these parameterizations that you have to deal with these piecewise functions. So notice as t increases from 0 to 1, how would you describe the x-coordinates and the y-coordinates in that first section of the graph?
Y equals 0.
Yeah. Y equals 0 and x equals t.
T, okay, I was going to say all those numbers here.
Yeah. And then as I go along here, I want to say cosine and sine. That was my intention when I chose to go from 0 to pi over 2. So, but I have to kind of adjust it so that I actually am plugging in 0 and pi over 2. So I'll just say
Oh,
right.
I see, yeah.
So now I'm beginning, when t equals 1, I'm plugging in 0.
0.
When t equals pi over 2,
1 plus
or no,
minus 1.
when t equals 1 plus pi over 2, the minus 1 makes it just pi over 2.
Mm-hmm.
So I can begin and end exactly where I want it to begin and end. So I'm just kind of shifting it a little bit. And then along here, you can see how along here that it's always x coordinates always 0.
X equals 0 and then y equals 2.
Almost, except t is starting here and ending there.
Okay, absolutely.
And notice as you move through this interval, t is getting bigger, but along here, t is getting smaller. That's a little bit tricky. I need to reverse the orientation of t and shift it. Yeah. Reversing just means a negative.
Right. I got that part.
Yeah, dragging.
Some parentheses help. I'm going to do a t. How about I go with, let me think, what do I want? Minus two plus pi over 2? Let me see. Usually I take a stab at it. Most of the time it's not right, but once I can see why it's not right, I can see how to fix it. So if t was equal to, so when t equals 1 plus pi over 2, I want to be here. I want the y-coordinate to be 1.
Right.
So if t equals 1 plus pi over 2, that's 1 plus pi over 2 minus 2 plus pi over 2. Pi over 2 is canceled. 1 minus 2 is negative 1, and this makes it positive. So it looks promising. And then when I get to here,
0.
yeah, it's that minus that is 0. And so it ends up right where I wanted it to be. So I think that'll do it actually. All right. Pretty weird. But we'll be we won't be doing as much with that, as far as I know, in this class. It's something, so when you get to multivariable, you'll be revisiting parameterizations, and you'll have to do some stuff like that. You'll be, in there, you'll be doing these line integrals. You know, an integral, not along the x-axis, but along this curve. So, kind of interesting.
My head started hurting earlier.